What if the first chapter of Earth's biological history was actually written on Mars? It is a question that challenges our assumption of isolation. Planetary science shows that Mars cooled and settled hundreds of millions of years before our own planet, potentially creating habitable conditions while Earth was still molten. Through cosmic impacts, rocks have traveled between these worlds, carrying the chemical ingredients necessary for life. We aren't looking at science fiction, but rather the physics of planetary exchange. If this shift in perspective engages your mind, a quiet like and subscribe helps us continue. You're listening to Fall Asleep with Science, and tonight we'll examine the evidence suggesting we might all be descendants of the Red Planet. Scientists have spent generations investigating the origins of biology, seeking to unravel how inanimate molecules organize themselves into the intricate, self-replicating systems we know as living organisms. For a long time, the assumption was that this extraordinary phenomenon occurred exclusively on Earth. However, as we uncover more about the ancient history of the Red Planet, a different narrative begins to emerge. Tantalizing clues suggest that billions of years ago, Mars may have been a more promising environment for life than our own planet. To understand this possibility, we must look at the physics of planetary formation. Mars cooled faster than Earth. Its surface likely harbored liquid water earlier, and its chemical composition may have been particularly suited for jump-starting biological processes. This leads to a compelling hypothesis. Rather than being Earth's lesser twin, perhaps Mars was the elder sibling that sparked life in the solar system, only for that life to migrate here later. To evaluate this, one must first examine the conditions of the early solar system. Billions of years ago, our young solar system was a chaotic and violent place. Planets were still forming, colliding with debris left over from the solar nebula. Among this celestial tumult, Mars stood out. Unlike Earth, which was still in the throes of its molten infancy, Mars stabilized relatively quickly. This rapid cooling allowed the crust to harden and liquid water to flow on its surface. This was an essential ingredient for life as we understand it, potentially creating a hospitable environment long before Earth's surface became temperate. The early Martian atmosphere was likely much denser than the thin veil of gas that surrounds the planet today. A thicker atmosphere would have created a greenhouse effect, trapping heat and warming the planet enough to allow water to persist in lakes, rivers, and perhaps even shallow seas. Geological evidence gathered by missions like NASA's Perseverance and Curiosity rovers supports this view. These machines have photographed ancient riverbeds, deltas, and sedimentary layers that tell a definitive story of a wetter, more temperate Mars. If these conditions existed billions of years ago, they could have supported the chemistry needed for life to emerge. The landscapes of Mars, now barren and desolate, may once have been cradles of life, nurturing primitive microorganisms in their primordial waters. The chemical composition of the planet further strengthens the case for its habitability. On Earth, active plate tectonics and geological activity constantly recycle the crust, melting down old rocks and erasing the past. Mars, lacking this aggressive tectonic activity, preserves its ancient chemical history. It offers a snapshot of the planet as it was billions of years ago. Among the most compelling discoveries is the presence of phosphorus and boron. These are critical elements for the formation of RNA, one of the fundamental building blocks of life. These elements have been found in Martian meteorites and analyzed by rovers on the surface, suggesting that Mars possessed the raw materials needed to catalyze the origins of biology. Moreover, The abundance of iron, sulfur, and silica on Mars creates an environment ripe for prebiotic chemistry. Laboratory experiments here on Earth show that such minerals can facilitate the assembly of complex organic molecules. On ancient Mars, these processes could have been accelerated by volcanic activity and the interaction of water with the mineral-rich crust. In addition, the discovery of organic molecules by the Curiosity rover hints that Mars was once a chemically dynamic environment. It was capable of sustaining the complex reactions required for life to emerge. But this leads to a logical progression. Even if life did originate on Mars, how could it have traveled to Earth? This question leads us to the concept of panspermia. This is the scientific theory that life, or the chemical precursors of life, can be transported between planets via meteoroids. In the early years of the solar system, massive impacts were common. Large asteroids striking Mars would have ejected rocks into space with tremendous force. Some of these rocks would enter orbit around the Sun and eventually cross paths with Earth, landing as meteorites. Today, scientists have identified dozens of Martian meteorites on Earth. We know they are from Mars because they contain trapped gases identical to the signature of the Martian atmosphere. Could these meteorites have carried with them the seeds of life, or at least the building blocks necessary to kickstart it on Earth? This hypothesis gains credibility when we consider the resilience of microbial life on our own planet. We have discovered extremophiles, which are organisms capable of surviving in the harshest environments imaginable. These microbes thrive in conditions once thought impossible for biology to sustain. Experiments have shown that certain microbes can endure the vacuum of space, intense radiation, and extreme temperatures. If life began on Mars, it is conceivable that primitive microorganisms could have survived the interplanetary journey embedded deep within a rock, arriving on Earth to find a hospitable new home. Proposing that life began on Mars before Earth challenges deeply ingrained assumptions about our planet's uniqueness. For centuries, Earth has been viewed as the focal point of life in the cosmos, a singular world in a universe of lifeless orbs. But if Earth's biosphere owes its origins to Mars, then life is not an Earth-centric phenomenon. It may be a cosmic inevitability, arising wherever conditions permit. This paradigm shift would have profound implications for our understanding of life's place in the universe. Skeptics argue that the evidence for Martian life remains circumstantial. They point out that Earth's more dynamic geological and atmospheric systems make it a more likely cradle of life, despite the delayed cooling. However, this perspective does not preclude the possibility that Mars played a role. The interplay between Mars and Earth in the early years of the solar system was likely far more interconnected than we once believed. The two planets exchanged materials and perhaps even biological matter across eons. As we continue to explore the Red Planet, the search for definitive proof of past or present life takes center stage. Missions like Perseverance are equipped to analyze rock samples in unprecedented detail. They are seeking biosignatures, which are chemical markers that could indicate biological processes. Future missions, including the highly anticipated Mars sample return, aim to bring Martian rocks back to Earth for analysis in state-of-the-art laboratories. These efforts represent humanity's most ambitious attempt yet to answer one of the greatest questions of all time. Are we the cosmic descendants of a Martian ancestor? If life is found on Mars, even in its simplest microbial form, it would revolutionize our understanding of biology and planetary science. The discovery would confirm that life can arise independently in multiple locations, or that it can travel between stars. This strengthens the case for life existing elsewhere in the universe. But to truly understand how this could happen, we must look at the dynamics of the early solar system. The story of life as we know it begins in the chaos of the early solar system. This was a time when our sun was just a fledgling star, surrounded by a swirling nebula of gas and dust. From this cosmic nursery, the planets emerged. They were forged in a crucible of collisions, chaos, and unimaginable heat. It was a violent epoch, but also one filled with potential. It was a time when the building blocks of life were scattered across the nascent solar system, waiting to seed worlds like Earth and Mars. In those primordial times, physics dictates that the red planet may have experienced its own flourishing age of habitability, hosting the earliest sparks of life. 4.5 billion years ago, the sun was born from the gravitational collapse of a massive cloud of gas and dust. As the sun ignited at its core, the surrounding material flattened into a protoplanetary disk. Within this disk, tiny grains collided and stuck together. They grew into pebbles, then boulders, and eventually planetesimals. These planetesimals were the building blocks of planets. They collided with one another, their immense energy melting their surfaces and allowing heavier elements like iron to sink to their cores. Over millions of years, these repeated impacts gave rise to the rocky planets, including Earth and Mars. This was not a peaceful process. The young solar system was a chaotic dance of collisions, with planetesimals smashing into forming planets and each other. Some were obliterated, while others grew larger with every impact. It was in this violent crucible that the unique trajectories of Earth and Mars were set, defining their paths for billions of years to come. Despite their shared origins, Mars and Earth embarked on very different developmental timelines. One of the most critical factors in this divergence was size. Mars is only about half the diameter of Earth. Because of this smaller mass, it cooled far more quickly, while Earth's larger mass retained its heat, keeping its surface molten for millions of years longer. Mars rapidly developed a stable crust. This stability allowed the formation of liquid water on its surface far earlier than on Earth. The smaller size of Mars also meant that its volcanic activity subsided sooner, and its weaker gravity struggled to retain a thick atmosphere over billions of years. In contrast, Earth's ongoing volcanism released vast quantities of gases that formed a dense, protective atmosphere. However, it took much longer for conditions on Earth to stabilize enough for life to emerge. For Mars, this early cooling presented a unique opportunity, creating what some scientists call its ancient habitability window. Billions of years ago, Mars was likely a world of rivers, lakes, and possibly even oceans. Its surface was warmer and wetter than the cold, arid desert we see today. Evidence of this ancient climate is etched across its surface in the form of dried riverbeds, sedimentary layers, and delta formations. While Earth was still a molten inferno, Mars may have been hosting stable bodies of liquid water, a critical ingredient for life. During this period, the red planet's atmosphere, though thin by Earth standards, likely provided sufficient warmth for liquid water to persist. Coupled with the heat generated by volcanic activity and the presence of essential elements like carbon, hydrogen, nitrogen, and phosphorus, Mars had all the ingredients needed for prebiotic chemistry. If life began anywhere in the solar system, this early Mars, teeming with potential, was an ideal candidate. The story of life's emergence on Mars and later on Earth cannot be told without understanding the role of asteroids and comets. These celestial messengers bombarded the inner planets during the solar system's infancy, delivering water, organic molecules, and other life-building materials. It is believed that these impacts played a critical role in shaping the environments of both Mars and Earth. Mars, with its proximity to the asteroid belt, may have received a different mix of materials than Earth. The impacts themselves created temporary habitats, hydrothermal systems formed at impact sites, where the heat from the collision interacted with water in the crust. These hot, water-rich environments could have provided the perfect conditions for the synthesis of complex organic molecules, perhaps even the first primitive life forms. Earth, meanwhile, was not so fortunate during its earliest days. The sheer intensity of asteroid impacts likely vaporized any nascent oceans and sterilized the planet's surface multiple times. While Mars was enjoying a period of relative calm and stability, Earth was locked in a cycle of destruction and recovery, delaying the onset of habitable conditions. Around 4 billion years ago, the solar system experienced a cataclysmic event known as the Late Heavy Bombardment. This period was characterized by an intense barrage of asteroids and comets that reshaped the surfaces of the inner planets. For Earth, the Late Heavy Bombardment may have been both a curse and a blessing. On one hand, the impacts likely delayed the emergence of stable environments by sterilizing large portions of the planet. On the other hand, the influx of water and organic materials provided by these celestial impacts laid the groundwork for future habitability. Mars, with its smaller size and thinner atmosphere, may have experienced the Late Heavy Bombardment differently. While its surface was also pockmarked with craters, the relative lack of tectonic activity on Mars meant that many of these ancient scars remain visible today. This offers scientists a window into this turbulent period. Could it be that the Late Heavy Bombardment, while destructive, provided Mars with the final push it needed to transition from a merely habitable world to a potentially inhabited one? The dynamic forces of the early solar system raise an intriguing question. If life began on Mars during its ancient habitability window, could it have been transported to Earth via meteorites? Scientists have identified Martian meteorites on Earth, ejected from the red planet by asteroid impacts and later falling to our planet's surface. If microbial life existed on Mars during this time, it is conceivable that these spacefaring rocks carried living organisms, or at least the precursors of life, to Earth. This idea, known as lithopanspermia, suggests a shared origin for life on Earth and Mars. In this scenario, Mars acted as the cradle of life, with Earth eventually inheriting the legacy of its neighbor. While this remains a theory, ongoing studies of Martian meteorites continue to search for traces of ancient life or organic materials that could support this remarkable possibility. Today, Mars is a shadow of its former self. Its ancient lakes and rivers have long since dried up. Its atmosphere has been stripped away by solar winds. Yet, the evidence of its habitable past endures, waiting to be uncovered by robotic explorers and perhaps one day, human missions. The story of early solar system dynamics reminds us that Mars was not always the barren world we see today. It was once a world of possibility, a silent witness to the birth of life, or perhaps its earliest host, Mars, an ancient oasis. Mars has long captured the imagination of humanity, not just as a neighboring planet, but as a world that might once have been alive. Billions of years ago, the red planet wasn't the dry, barren landscape we see today. Instead, evidence suggests it was a world rich with water, harboring rivers, lakes, and possibly even oceans. These features, coupled with a climate that might have been far more hospitable, make Mars one of the most compelling candidates for understanding the conditions necessary for life. The ancient landscape of Mars tells a very different story from its current desolation, a story of flowing water and dynamic geological processes. River valleys snake across the terrain, carved out by liquid water billions of years ago. These networks of dried-up riverbeds suggest that surface water once flowed consistently, possibly over millions of years. Craters like Gale and Jezero show clear evidence of deltas, which are sedimentary formations created by rivers emptying into lakes. These features indicate a time when water pooled in great basins, forming lakes that could have supported life. Layered sedimentary deposits in these regions point to slow-moving waters shaping the surface and creating habitats that may have been ideal for microbes. Other geological features reinforce the narrative of Mars as a watery world. Alluvial fans, formed by debris washed down by water, hint at episodic flooding events that transported materials across the planet's surface. Even impact craters, the scarred reminders of violent collisions, show erosion patterns consistent with flowing water. In more recent observations, scientists have detected recurring slope lineae, dark streaks on Martian slopes that may represent seasonal water flows or brine seeping to the surface. Together, these features paint a vivid picture of ancient Mars as a world where water wasn't just present, but abundant. To sustain such an environment, Mars would have needed a climate far different from its current freezing, desiccated state. Billions of years ago, Mars was warmer and wetter, conditions that would have allowed liquid water to persist on its surface. At that time, the young sun was less luminous, but Mars's position near the snow line, a region in the solar system where water ice is stable, meant it could take advantage of modest warming from greenhouse gases. Geological evidence suggests that volcanic activity released significant amounts of carbon dioxide and water vapor into the atmosphere. This created a greenhouse effect that trapped heat and kept surface temperatures above freezing. Climate models of ancient Mars also point to cycles of rainfall or snowmelt, which would have further shaped its terrain. These wetter conditions likely fluctuated, with periods of aridity, followed by episodes of abundant water. Volcanic eruptions, releasing ash and gas into the atmosphere, might have periodically warmed the planet, melting ice and jump-starting water flow. The atmosphere, far thicker than it is today, would have played a crucial role in regulating these processes. The thick atmosphere that once enveloped Mars was a cornerstone of its ability to support liquid water. Today, the atmosphere is a thin, fragile shell, but billions of years ago, it was dense enough to maintain surface pressure conducive to liquid water. Studies of Martian meteorites and surface isotopes suggest the planet had a nitrogen-rich atmosphere with traces of argon and other gases. This atmospheric density would have not only supported liquid water, but also shielded the surface from harmful cosmic radiation, creating an environment that could sustain life. Over time, the planet's magnetic field, which protected its atmosphere from the solar wind, weakened and eventually disappeared. Without this shield, solar wind stripped away the atmosphere, thinning it to the tenuous state we see today. This loss of atmosphere likely marked the end of Mars's ability to support liquid water on its surface, driving the planet into its current arid state. But before this decline, Mars may have boasted features that rivaled Earth's oceans. Scientists hypothesize that vast oceans once covered the planet's northern hemisphere. These ancient Martian seas might have contained enough water to cover the entire planet to a depth of hundreds of meters. Shorelines identified through topographic mapping suggest the northern lowlands could have been a giant ocean basin. Sedimentary deposits along these shorelines point to persistent bodies of water that existed for millions of years, creating environments potentially teeming with life. Even as Mars transitioned to a colder climate, water may have persisted in underground reservoirs. Evidence from radar scans and rovers has revealed large deposits of subsurface ice, remnants of the planet's wetter past. These ice layers, some buried beneath protective layers of dust and rock, represent Mars's hidden water history. The presence of subsurface aquifers raises intriguing questions about whether life could still exist, buried beneath the surface and insulated from the harsh environment above. To understand Mars's watery history, it is essential to compare it to early Earth. Both planets began with similar ingredients: volcanic activity, water, and essential elements for life. However, their evolutionary paths diverged due to differences in size, gravity, and geological activity. Earth's tectonic plates recycled carbon dioxide, stabilizing the climate and supporting a long-term water cycle. Mars, with its smaller size and weaker gravity, lost its tectonic activity earlier, limiting its ability to sustain a stable climate. Despite these differences, Mars's ancient lakes and river systems bear a striking resemblance to early Earth environments. The deltas and sediment layers found in Martian craters are analogous to those on Earth during its Precambrian era, when microbial life flourished. These similarities suggest that Mars could have hosted life during its habitable phase, raising questions about the universality of biology in the universe. Mars's ancient water story is also written in its rocks and minerals. Hydrated minerals such as clays and sulfates, found across the planet's surface, provide direct evidence of prolonged water activity. These minerals form in the presence of water, pointing to stable environments where water interacted with the Martian crust. Perchlorates discovered in the soil by rovers hint at briny water flows that may have persisted even as Mars became colder and drier. The discovery of silica and hematite-rich deposits further supports the theory that Mars once had liquid water with neutral to slightly acidic pH, conditions favorable for microbial life. Volcanic activity on Mars also played a significant role in shaping its water history. Eruptions released water vapor and other gases, contributing to a temporary greenhouse effect that warmed the surface. Evidence of ancient hydrothermal systems, places where heat from the planet's interior interacted with water, points to potential habitats for life. These hydrothermal vents, similar to those on Earth's ocean floor, could have provided the energy and nutrients necessary for life to thrive. While water once flowed freely on Mars, its availability wasn't uniform. Regional variations in the landscape created diverse water systems, from vast oceans in the north to isolated lakes and craters. The southern highlands, with their higher elevation, likely hosted ice and small glacial systems, while the northern lowlands acted as basins for larger water bodies. These regional differences would have shaped Mars's climate and hydrology, creating a patchwork of environments with varying potential for habitability. The loss of water on Mars wasn't immediate. For millions of years, water may have cycled between the surface and underground reservoirs. Seasonal changes driven by Mars's axial tilt influenced the stability of liquid water, creating transient rivers and lakes. Dust storms, a defining feature of modern Mars, likely played a role in redistributing water and affecting its long-term availability. The interplay between surface water and atmospheric loss created a dynamic system, one that eventually succumbed to the planet's harsh conditions. Mars's history as a watery world is more than a geological curiosity. It is a testament to the planet's potential to harbor life. If microbial life ever emerged on Mars, it would have found a home in its stable lakes, beneath its protective atmosphere, or near hydrothermal vents. Understanding these ancient environments is crucial for future missions, as scientists search for biosignatures, chemical traces of life that may still be preserved in Martian rocks. As we explore Mars through rovers and orbiters, the story of its ancient water continues to unfold. Curiosity has uncovered clay-rich regions in Gale Crater, pointing to a long-lived lake environment. Perseverance is now exploring Jezero Crater, a former river delta, in search of signs of past life. Mars's transformation from a vibrant, water-rich world to the arid desert we see today is a reminder of how dynamic planets can be. This brings us to the organic chemistry on Mars and the building blocks of potential life. The discovery of organic molecules on Mars is not just a milestone. It is a doorway to understanding whether life once existed or could still exist on our planetary neighbor. Through advanced missions and tireless exploration, we have begun to unravel the chemical mysteries buried in Martian soil, rocks, and atmosphere. The groundbreaking detection of organic compounds by NASA's Curiosity rover in Gale Crater marked a significant leap forward in our understanding of Mars. In 2018, the rover unearthed a treasure trove of simple organic molecules trapped within ancient mudstones. These molecules, such as thiophenes and aliphatic hydrocarbons, are not definitive evidence of life but serve as the building blocks for biological processes. Their discovery is significant because it proves that the chemical ingredients necessary for life were present on Mars billions of years ago. Curiosity's detection revealed that these molecules were preserved in sediments from an ancient lakebed, highlighting Gale Crater's potential as a once habitable environment. These organics could have originated from Martian biology, meteorite impacts, or even geological processes, such as volcanic activity. The finding challenges us to dig deeper into Mars's chemical history. Among the most debated discoveries on Mars is the presence of methane in its atmosphere. Methane is a volatile gas that on Earth is produced predominantly by biological activity. On Mars, the story is more complex. Seasonal fluctuations in methane levels have been detected by both the Curiosity rover and orbiters like the European Space Agency's Trace Gas Orbiter. These patterns suggest that methane is being released periodically, possibly from underground reservoirs. The source of Martian methane remains a mystery. It could arise from abiotic processes like serpentinization, where water interacts with certain minerals, or it could hint at microbial life lurking beneath the surface. The short lifespan of methane in Mars's atmosphere further complicates the puzzle, indicating recent or ongoing activity, whether geological or biological. The presence of methane hints at a dynamic, active Mars. Volcanic activity on Mars has played a crucial role in shaping its chemical landscape. Billions of years ago, the planet was home to massive volcanic eruptions that released carbon dioxide, sulfur, and water vapor into the atmosphere. These elements created a rich chemical environment, potentially fostering prebiotic reactions necessary for life. Hydrothermal systems associated with volcanic activity may have provided energy and nutrient-rich conditions similar to those found around Earth's deep-sea vents. These environments could have acted as chemical crucibles where organic molecules formed and accumulated. The legacy of this activity is imprinted in Mars's basaltic rocks, which hold clues to the planet's fiery past and its potential for habitability. Mars's soil is rich in perchlorates, chemical compounds that have sparked both excitement and challenges in the search for organics. Discovered by NASA's Phoenix lander in 2008, perchlorates are highly reactive oxidizing agents that can break down organic molecules when heated. This characteristic makes it difficult to detect organics directly, as the compounds might decompose during analysis. Despite their destructive property, perchlorates may also serve as a source of chemical energy for microbes. On Earth, certain extremophiles thrive by metabolizing perchlorates, suggesting that similar organisms could exist on Mars. These compounds are a paradox, both a hindrance to our investigations and a potential lifeline for Martian life. While the chemistry of the soil presents challenges, the survival of potential life on Mars is fundamentally tied to the loss of its planetary protection. Mars's ancient magnetic field once played a vital role in shielding its surface from harmful solar radiation, allowing organic molecules to form and persist. However, when the magnetic field weakened and vanished approximately 4 billion years ago, Mars became vulnerable. Without this shield, cosmic rays and solar winds stripped away much of the atmosphere, destroying surface organics. Today, any remaining organics on the Martian surface are likely buried beneath layers of rock and regolith, shielded from radiation. These subsurface environments, protected from harsh conditions, offer a promising refuge for life or its chemical remnants. Future missions will likely focus on drilling into these hidden reservoirs to uncover their secrets. Mars's history of hydrothermal activity presents another possibility for organic chemistry. Evidence suggests that ancient hydrothermal vents existed, providing a continuous source of heat and nutrients. These vents could have created localized environments conducive to prebiotic chemistry, where complex organic molecules formed and interacted. On Earth, similar systems are teeming with life, making them one of the most promising analogs for potential Martian ecosystems. Mars's surface has also been shaped by meteoritic impacts, which delivered a steady supply of organic-rich material from space. Carbonaceous chondrites, a type of meteorite, are known to contain amino acids and other organic compounds. These impacts may have deposited essential ingredients for life on the Martian surface. High-energy impacts also generate heat and pressure, facilitating chemical reactions that can synthesize new organic molecules. Impact craters such as Gale and Jezero are thus not just geological landmarks. They are potential laboratories for prebiotic chemistry. The link between the amounts of oxygen and methane in Mars's atmosphere is one of the most fascinating findings of the past several years. The Curiosity rover recorded seasonal changes in both gases at the same time. These pulses suggest an active planet, and while photochemical processes triggered by ultraviolet light are one non-biological explanation, the connection raises the intriguing prospect of microbial life beneath the surface. Understanding these cycles is an important goal for ongoing missions. Despite significant advancements, detecting organics on Mars remains a formidable challenge. The planet's oxidizing surface environment, dominated by reactive compounds like perchlorates, complicates direct analysis. Instruments must be capable of distinguishing between biological and abiotic sources while avoiding contamination from Earth. Missions like Perseverance and the upcoming Mars Sample Return aim to address these challenges by collecting and analyzing pristine samples, representing a critical step toward unlocking the secrets of Martian organics. The role of Martian minerals as the building blocks of life is crucial. The old rocks conceal a narrative, while the landscape and towering volcanoes appear desolate now. The chemistry within them tells a different story. Phosphates, boron, sulfur, and iron are among the minerals buried beneath the rust-colored soil, which may have created the perfect setting for the first sparks of life. At the heart of life as we know it is RNA, the molecular precursor to DNA. Phosphate is the sturdy backbone for RNA molecules. Mars has an abundance of phosphate-bearing minerals like apatite. These minerals likely dissolved in ancient Martian waters, making phosphates bioavailable in concentrations that may have outpaced Earth's early environments. What sets Mars apart is its unique water chemistry. Mars's waters were rich in acidic solutions. This acidity likely dissolved phosphates, releasing them and making them more readily available for chemical reactions. This distinct geochemical advantage might have allowed Mars to support prebiotic chemistry earlier than Earth. Another critical discovery was boron, an element essential for stabilizing ribose, the sugar molecule in RNA. Boron acts as a molecular stabilizer, preventing ribose from degrading in aqueous environments. While boron is relatively scarce on Earth, Mars may have had more accessible borates thanks to its volcanic activity and unique mineral composition. This raises a compelling question. Did Mars's natural abundance of boron make it a more favorable cradle for life's molecular precursors? Mars owes its iconic red hue to the abundance of iron on its surface. Iron was not just a geological feature. It may have been a biochemical catalyst. Iron's ability to drive redox reactions, the transfer of electrons between molecules, makes it a powerful enabler of prebiotic chemistry. Ancient Martian waters likely carried dissolved iron, creating a dynamic environment where organic molecules could form and interact. Sulfur, another essential element for life, is also found in abundance. Sulfur plays a pivotal role in metabolic processes. On Mars, sulfur may have driven the chemistry necessary for early life. Sulfates are highly soluble in water, creating reactive environments. Volcanic activity likely released sulfur into the atmosphere and into ancient lakes, creating hotspots of chemical activity analogous to Earth's hydrothermal vents. Silicon, a major component of Martian rocks, and its related clay minerals, or phyllosilicates, add another layer of intrigue. Silicate minerals provide reactive surfaces that can concentrate organic molecules, acting like natural laboratories. Clays are known catalysts for organic chemistry, absorbing simple molecules and concentrating them into small areas, increasing the likelihood of reactions. Fragile organic molecules may have found the stability they required to develop into the ancestors of life within the protective embrace of these clay particles. The geological stability of Mars is an enthralling feature in itself. Much of Mars's old mineral record has survived. In contrast to Earth's surface, which is continually changing due to plate tectonics, Mars has been relatively quiet. Due to this stability, the early solar system history provides information that the Earth's dynamic crust has long ago covered up. Mars's mineral wealth, combined with its stable geology, created a unique environment for chemical evolution. Its early oceans, acidic waters, and volcanic activity may have created a more favorable setting for prebiotic chemistry than Earth's more turbulent beginnings. Volcanoes on Mars were chemical engines. The planet's sulfur dioxide, carbon dioxide, and water vapor atmospheres were formed by the planet's tremendous volcanic activity. Reactive habitats rich in varied components were created as a result of these gases interacting with the surface. Volcanic glass, a byproduct of eruptions, is particularly interesting because this material is highly reactive and can facilitate the assembly of organic molecules. The rocks of Mars provide evidence of the red planet's wet history, from hydrated minerals like gypsum to extensive systems of old riverbeds. These minerals also serve as reservoirs, encasing liquid and dissolved organics inside their frameworks, maintaining constant conditions necessary for the chemistry of life to endure. Mars's lack of tectonic activity has preserved its ancient mineral record, making it a time capsule of the early solar system. We do not always need to go to Mars to study it. Sometimes, Mars comes to us. Martian meteorites are rare treasures, identified by their unique geochemical fingerprints, which match the composition of gases In Mars's atmosphere, these rocks, numbering fewer than 300, are fragments of Mars's crust that were blasted into space by asteroid or comet impacts. Over millions of years, some traverse the solar system, eventually crossing Earth's orbit and surviving the fiery descent through our atmosphere. Among the most famous is ALH 84001, found in Antarctica in 1984. Estimated to be over 4 billion years old, it contains carbonate globules that sparked widespread interest. When NASA scientists announced in 1996 that the structures inside might be evidence of ancient Martian life, the world took notice. Researchers identified features resembling microfossils. However, skepticism soon arose, contending the features may have developed as a result of post-meteorite pollution or abiotic processes. Despite the ongoing discussion, ALH 84001 remains an important piece of evidence in the hunt for extraterrestrial life. The journey of these meteorites begins with violent cosmic events. Mars's relatively low gravity and thin atmosphere make it easier for rocks to escape its grasp compared to Earth. Once ejected, these rocks embark on a perilous journey, surviving intense radiation and the vacuum of space for millions of years. Remarkably, some still contain traces of water-altered minerals and organic compounds. The existence of Martian meteorites on Earth raises a tantalizing question. Could life have originated on Mars and been transported to Earth via meteorites? This idea is central to the panspermia hypothesis, which posits that life, or the building blocks of life, can travel between planets, hitching rides on spacefaring rocks. Laboratory experiments have shown that microbial life can survive the intense heat of atmospheric entry when shielded within rocks. If life existed on Mars during its early habitable phase, meteorite transfer could have provided a pathway for Martian microbes to seed life on Earth. Scientists classify Martian meteorites into 3 main groups: shergottites, young volcanic rocks; nakhlites, older rocks with evidence of water alteration; and chassignites, rare samples revealing mantle composition. Together, they highlight the diversity of Martian meteorites and underscore their value as records of the planet's evolution. The finding of organic compounds in meteorites from Mars is one of the most fascinating findings in this field. Yet their provenance is a matter of heated controversy. Are these organics the product of abiotic Martian processes, or the remains of a bygone Martian civilization? Is it also possible that they were exposed to organics after touching down on Earth? Advanced analytical techniques, such as isotopic analysis, have provided some answers, but also raised new questions. The isotopic signatures of certain organic molecules suggest they originated on Mars, strengthening the case for indigenous Martian chemistry. Yet the possibility of contamination cannot be entirely ruled out, illustrating the challenges of interpreting these enigmatic samples. Beyond the search for life, Martian meteorites offer invaluable information about Mars's ancient environment. Traces of water-altered minerals and trapped atmospheric gases provide direct evidence that Mars once had liquid water and a thicker atmosphere. These findings align with observations from Mars rovers and orbiters, which have identified river valleys, deltas, and other features indicative of a wetter past. Research into meteorites has also shown that throughout the course of billions of years, Mars's environment changed substantially. From what appears to be a warm and humid planet, it was eventually transformed into a cold and dry one due to volcanic eruptions subsiding, the planet's magnetic field vanishing, and atmospheric erosion caused by solar winds. Scientists can better piece together Mars's past and assess the red planet's habitability if they have a better grasp of these processes. Studying Martian meteorites is no small feat. These rocks are rare, and their journey through space and time has left them altered in ways that complicate analysis. Contamination from Earth's environment is a persistent challenge, as is the difficulty of determining the age and origin of specific features within the meteorites. Despite these hurdles, advances in technology continue to yield new insights. Modern spectroscopic techniques, for example, have revealed details about the mineralogy and chemistry of Martian meteorites that were previously inaccessible. The rewards of this research are immense. Martian meteorites are not just geological specimens. They are windows into the past, offering clues about the conditions that shaped Mars and potentially fostered life. They also serve as stepping stones for future exploration, guiding the design of Mars missions and informing the search for biosignatures on the Red Planet. The study of Martian meteorites is far from over. As scientists continue to analyze existing specimens and discover new ones, the mysteries of Mars will gradually come into sharper focus. Upcoming Mars sample return missions promise to provide fresh context for interpreting meteorite findings, potentially resolving long-standing debates and opening new avenues of inquiry. For centuries, humanity has pondered the origins of life on Earth. But what if the story began elsewhere, on a neighboring world, with matter hurtling through space to seed our own planet? This is the intriguing premise of the panspermia hypothesis, a theory that suggests life or its precursors may travel between planets, carried by meteorites, or even propelled by cosmic forces. Panspermia, meaning seeds everywhere, was first conceptualized by the ancient Greek philosopher Anaxagoras. Its scientific foundation took root much later, when thinkers like Svante Arrhenius proposed that microscopic life could travel between celestial bodies. Modern science has reinvigorated the variation known as lithopanspermia life, traveling via rocks with evidence of organic molecules on comets, extremophiles surviving space-like conditions, and Martian meteorites bearing hints of organic compounds. Panspermia is no longer confined to the realm of speculation. The journey of life between planets is fraught with peril. Space is a vacuum, bombarded by radiation and subjected to extreme temperatures. Yet certain microorganisms on Earth, extremophiles, seem almost custom-built for such journeys. Take Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium for its remarkable resilience to radiation. Then there are tardigrades, tiny creatures known as water bears, which have endured the vacuum of space unscathed. These hardy organisms provide proof of concept that life can endure the conditions of interplanetary transit. Laboratory experiments have further bolstered this possibility. NASA's LDEF, Long Duration Exposure Facility, and ESA's Biopan missions exposed microbial spores to space-like conditions, finding that some survived prolonged exposure. Encased within meteorites or ice, these microorganisms could be shielded from radiation, significantly enhancing their survival odds. The mechanics of panspermia hinge on the ejection of material from a life-hosting planet into space. This is where cosmic impacts come into play. When a large asteroid or comet strikes a planet, it can send debris flying into space at incredible velocities. On Mars, with its lower gravity compared to Earth, this process is even more efficient. Simulations show that fragments of Mars's surface containing potential microbes or organic molecules could easily escape its gravitational pull. Once ejected, these fragments become cosmic travelers, drifting through the solar system. Some of this Martian debris has made its way to Earth, as evidenced by meteorites like ALH84001. These space rocks carry chemical and isotopic signatures uniquely Martian, showing that material exchange between planets is not just possible but has occurred. How panspermia fits in with the schedules of habitable planets is one of the most intriguing parts of the theory. Mars cooled more rapidly than Earth, meaning that it may have become habitable sooner. The early appearance of life on Earth might be explained by the transport of germs from Mars to Earth via meteorites. Assuming this is indeed the case, studies suggest that Martian material ejected by impacts could reach Earth in tens of thousands of years, a time frame short enough for hardy microorganisms to survive the journey. Some fragments could even remain in stable orbits for millions of years, creating opportunities for multiple waves of transfer. While the hostile environment of space is a big obstacle for panspermia, meteorites offer some natural defense. The majority of radiation may be absorbed by the exterior layers of a rock, protecting its inside. Studies have shown that microbial spores embedded in rocks or ice can survive simulated space conditions. These findings align with the hypothesis that life could hitch a ride across the cosmos encased in protective material. Panspermia, despite its allure, is not without skeptics. Critics argue that there is no direct evidence of microbial life on Mars or other celestial bodies, making the hypothesis speculative. They also question whether microorganisms could survive the intense heat of atmospheric re-entry. Counter-arguments abound. For one, extremophiles on Earth demonstrate that life can survive extreme conditions. Additionally, some meteorites retain material from their interiors, largely unaltered by re-entry, suggesting that embedded microorganisms could also survive. While Mars is the leading candidate for panspermia involving Earth, the hypothesis extends beyond our planetary neighbor. Comets, with their reservoirs of water ice and organic molecules, may also play a role. Missions like Rosetta, which studied comet 67P Churyumov-Gerasimenko, have detected complex organics, suggesting that comets could deliver life's building blocks to planets. Panspermia challenges our Earth-centric view of life's origins. If life can travel between planets, the cosmos becomes a much more interconnected web of potential habitats. This has profound implications for astrobiology, suggesting that life may be more common and more resistant than previously thought. As missions like Mars Sample Return and Europa Clipper prepare to collect and analyze extraterrestrial material, we may soon have the tools to test panspermia directly. Mars and Earth share similar origins, having formed around 4.5 billion years ago from the same primordial dust cloud. However, their evolutionary timelines diverged dramatically. Mars, being smaller and farther from the Sun, cooled more quickly than Earth. Geological evidence suggests that Mars entered a period of relative stability as early as 4.1 billion years ago. During this time, liquid water flowed on its surface, supported by a thick atmosphere that retained heat and pressure. Earth, on the other hand, was still in chaos for the first several 100 million years. It wasn't until around 3.9 billion years ago, during the tail end of the late heavy bombardment, that Earth began to stabilize. This lag in habitability gives Mars an intriguing edge in the timeline for life's emergence. Could Mars have nurtured life while Earth was still uninhabitable? On Earth, the earliest evidence of life comes from fossilized microbial mats known as stromatolites, dating back 3.5 billion years. These structures were created by colonies of cyanobacteria that thrived in shallow sunlit waters. Mars, too, had conditions that could have supported extremophiles during its early habitable window. The planet featured flowing rivers, vast lakes, and volcanic activity that provided heat and energy. If microbial life did emerge on Mars, it likely resembled Earth's early extremophiles. Water is a cornerstone of life, and its presence on both planets is key. Earth's vast oceans served as incubators. Mars, while lacking Earth's expansive seas, had its own reservoirs of liquid water. Ancient river valleys, lake beds, and deltas are etched into the Martian surface. The question is how long Mars could sustain liquid water. Its smaller size and weaker gravity made it difficult for the planet to hold on to its atmosphere. As its magnetic field dissipated, solar winds stripped away the atmosphere, causing surface water to evaporate or freeze. Yet, evidence of subsurface ice and hydrated minerals suggests that liquid water persisted long enough for life to potentially take hold. Life requires more than water. It needs energy. On Earth, early life harnessed energy through photosynthesis, chemosynthesis, or geothermal heat. Chemosynthetic microbes relied on chemical reactions involving sulfur, iron, and hydrogen to generate energy. Mars offered similar energy sources. Its volcanic activity, now dormant, would have created hot springs and hydrothermal vents, providing heat and nutrients. Iron and sulfur compounds in the Martian soil could have supported chemosynthetic organisms. While Earth was protected by its magnetic field and thick atmosphere, Mars lacked such defenses. As its core cooled and its magnetic field vanished, the Martian surface became vulnerable to solar and cosmic radiation. This poses a significant challenge for life on the surface. Beyond the search for life, Martian meteorites offer invaluable information about Mars's ancient environment. Traces of water-altered minerals and trapped atmospheric gases provide direct evidence that Mars once had liquid water and a thicker atmosphere. These findings align with observations from Mars rovers and orbiters, which have identified river valleys, deltas, and other features indicative of a wetter past. Research into meteorites has also shown that throughout the course of billions of years, Mars's environment changed substantially. From what appears to be a warm and humid planet, it was most likely turned into a cold and dry one due to volcanic eruptions subsiding, the planet's magnetic field vanishing, and atmospheric erosion caused by solar winds. Scientists can better piece together Mars's past and assess the red planet's habitability if they have a better grasp of these processes. Studying Martian meteorites is no small feat. These rocks are rare, and their journey through space and time has left them altered in ways that complicate analysis. Contamination from Earth's environment is a persistent challenge, as is the difficulty of determining the age and origin of specific features within the meteorites. Despite these hurdles, advances in technology continue to yield new insights. Modern spectroscopic techniques, for example, have revealed details about the mineralogy and chemistry of Martian meteorites that were previously inaccessible. The rewards of this research are immense. Martian meteorites are not just geological specimens. They are windows into the past, offering clues about the conditions that shaped Mars and potentially fostered life. They also serve as stepping stones for future exploration, guiding the design of Mars missions and informing the search for biosignatures on the red planet. The study of Martian meteorites is far from over. As scientists continue to analyze existing specimens and discover new ones, the mysteries of Mars will gradually come into sharper focus. Upcoming Mars sample return missions promise to provide fresh context for interpreting meteorite findings, potentially resolving long-standing debates and opening new avenues of inquiry. However, even as the surface became hostile, life could have found refuge underground. Subsurface environments insulated by layers of rock and soil, would have been shielded from radiation and could have provided stable conditions for microbial communities. On Earth, extremophiles like Deinococcus radiodurans demonstrate the resilience of life in high radiation environments. These microbes repair DNA damage caused by radiation, offering a potential model for how Martian life might have adapted. Subsurface ice and brines on Mars could still harbor microbial life, preserved in isolated pockets where radiation cannot reach. When it comes to fossil evidence, Earth has an undeniable advantage. Ancient stromatolites and microfossils provide direct proof of early microbial life. These fossils are often found in sedimentary rocks, where minerals have preserved the structures of microbial colonies. On Mars, the search for fossils is far more challenging. The planet's surface is exposed to constant erosion from wind and radiation, which degrades organic materials over time. Nevertheless, Mars rovers like Curiosity and Perseverance are equipped to detect biosignatures, chemical or structural markers of life. Clay minerals, silica deposits, and carbonate rocks on Mars are promising targets for finding preserved organic molecules. If microbial life existed on Mars, its fossils may still be hidden in the planet's ancient lake beds or underground. While both planets had the necessary ingredients for life, their long-term habitability diverged sharply. Earth's active geology and plate tectonics continuously recycled nutrients and maintained a dynamic climate. Mars, with its static crust and lack of tectonic activity, relied on volcanic outgassing and chemical weathering to sustain its environment. This difference likely influenced the complexity and persistence of life on each planet. Earth's oceans provided a stable, long-term habitat for life to evolve, while Mars's habitability was shorter and more episodic. The planet's rapid loss of atmosphere and water likely limited the window for life to develop beyond the microbial stage. However, if life did emerge on Mars, it may have left behind traces that await discovery. Among the more fascinating theories is the idea that Martian and earthly life may have originated from the same place. Panspermia is the idea that proposes the possibility of life or its components being transported to other planets via meteorites. It is possible that rocks with microorganisms on them were thrown into space by impacts on Mars and then crashed into Earth. Did life first emerge on Mars and then make its way to Earth? That is the intriguing question that this intergalactic interchange begs. Martian meteorites found on Earth, such as ALH 84001, contain organic molecules and mineral formations that some scientists interpret as potential biosignatures. While these findings remain controversial, they highlight the interconnectedness of our solar system and the possibility that life on Earth may owe its existence to Mars. From its early days as a warm, wet world to its current state as a frozen desert, Mars challenges us to rethink the conditions necessary for life and the resilience of biology. The importance of liquid water lies in its ability to dissolve and transport nutrients, facilitating the chemical reactions necessary for life. Its polarity enables it to act as a universal solvent, breaking down molecules and forming the basis for biological processes. Beyond its chemical properties, water's high heat capacity stabilizes climates, creating environments where life can thrive. If life ever existed on Mars, it would have required liquid water to sustain it, making the search for water a cornerstone of Martian exploration. Billions of years ago, Mars was a very different planet. Geological evidence suggests that vast oceans once sprawled across its surface. Scientists estimate that an ancient Martian ocean could have covered up to 20% of the planet's surface. with depths reaching thousands of meters. These waters likely pooled in the planet's northern hemisphere. But where did it all go? Over time, Mars's thin atmosphere and weak gravity allowed much of its water to escape into space or freeze beneath the surface. Mars is far from dry today. Subsurface ice deposits identified by radar instruments reveal vast reservoirs of frozen water. Seasonal cycles show water vapor in Mars's atmosphere rising and falling with changes in temperature. Perhaps most intriguingly, the European Space Agency's Mars Express mission detected what appears to be a subsurface lake of briny water beneath the planet's south polar ice cap. This discovery has reignited hopes of finding extant life, as such environments may provide refuge from Mars's harsh surface conditions. Our robotic explorers have provided compelling evidence of this watery past. The Curiosity rover discovered ancient stream beds in Gale Crater with rounded pebbles, indicating that water once flowed rapidly across the surface. In Jezero Crater, the Perseverance rover has been studying what was once a vast delta, where rivers deposited sediments into a long-gone lake. Meanwhile, Opportunity uncovered hematite blueberries, small mineral spheres formed in liquid water, further supporting the idea of prolonged wet conditions. Mars's surface is etched with features that speak of a watery past. The Valles Marineris Canyon system, the largest in the solar system, was likely carved by water erosion. Ancient deltas and river valleys point to persistent flowing water that could have supported life. Layered sediments found in these regions are similar to those seen on Earth, where water creates and preserves habitable niches. Mars's surface is rich in hydrated minerals, which form in the presence of water. Clay minerals and sulfates not only point to ancient water, but also serve as prime targets for future missions seeking signs of life. The chemical composition of Mars's ancient water is another key to understanding its habitability. Evidence suggests that early Martian water was less salty than it is today, with salinity levels conducive to life. However, as the planet dried out, its remaining waters became highly saline. The pH of Martian water is thought to have ranged from neutral to slightly acidic, conditions that would still have been favorable for microbial life. One of water's most important roles is its ability to preserve signs of life. On Earth, sedimentary rocks formed in water-rich environments often contain fossils. On Mars, similar sedimentary formations have been identified, particularly in ancient lakebeds and deltas. If life ever existed on Mars, these water-altered rocks could hold the key to its discovery. The upcoming Mars Sample Return mission aims to bring some of these samples back to Earth for detailed analysis. Billions of years ago, Mars may have had a functioning hydrological cycle, complete with precipitation, evaporation, and groundwater flow. This cycle would have supported a dynamic climate. However, as Mars's atmosphere thinned and its magnetic field disappeared, this cycle would have collapsed, leaving the planet cold and arid. Understanding this transition is critical for piecing together Mars's climatic history. Mars's decline from a wet, warm world to a frozen desert is largely attributed to atmospheric loss. Without a strong magnetic field to shield it, Mars's atmosphere was gradually stripped away by solar winds. This loss of atmospheric pressure made it impossible for liquid water to remain stable on the surface, forcing it to evaporate or freeze. Solar winds alone did not cause the dramatic transformation. High-energy ultraviolet radiation from the sun also played a role, causing photodissociation, breaking apart atmospheric molecules like carbon dioxide and water. This split water into hydrogen and oxygen. The lighter hydrogen atoms, unbound by gravity, escaped into space, while oxygen either bonded with surface minerals or drifted away more slowly. The isotopic composition of Mars's atmosphere tells the story of this escape. Heavier isotopes of elements like carbon and oxygen dominate the current atmospheric mix, as the lighter isotopes were preferentially lost to space. These isotopic ratios serve as a fingerprint of atmospheric erosion, allowing scientists to reconstruct the timeline of Mars's transformation. Data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission confirmed the rate at which solar winds continue to erode the Martian atmosphere. Mars's smaller size compared to Earth played a significant role in its atmospheric evolution. Its size meant that the planet cooled rapidly, leading to the solidification of its core and the cessation of volcanic activity. This cooling not only shut down the magnetic dynamo, but also reduced the outgassing of volcanic gases, which would have replenished the atmosphere. Volcanoes like Olympus Mons once released massive amounts of carbon dioxide, sulfur dioxide, and water vapor into the air, contributing to a thick, life-supporting atmosphere. Despite the significant decline, Mars's atmosphere is still dynamic. As volcanic activity dwindled, the planet's ability to maintain its atmospheric density also decreased. Seasonal dust storms, some of which envelop the entire planet, play a significant role in shaping its atmospheric behavior. These storms lift dust particles high into the atmosphere, where they interact with water vapor and other trace gases. This process accelerates the loss of water by allowing solar radiation to break apart water molecules more efficiently. Dust storms also create temperature and pressure fluctuations, showcasing the subtle interplay between the Martian surface and its atmosphere. Mars's polar ice caps, composed of water and carbon dioxide ice, act as seasonal reservoirs for its atmosphere. During the Martian summer, CO2 sublimates directly from the polar caps into the atmosphere, temporarily increasing its density. In winter, this gas refreezes at the poles, creating a cycle that affects surface pressure and weather patterns. As the atmosphere thinned, water either escaped into space or became trapped underground and in the polar ice caps. Some scientists speculate that subsurface reservoirs of liquid water may still exist, protected from the harsh surface conditions by layers of rock and ice. Methane detection on Mars has added a layer of intrigue to the story of its atmosphere. Observations by the Curiosity rover and orbiters have recorded seasonal variations in methane levels. This fluctuation hints at potential geological or even biological sources. Methane is a molecule that can be produced by microbial life, volcanic activity, or chemical reactions involving water and minerals. Its presence in the Martian atmosphere, albeit in trace amounts, raises questions about the planet's past and present habitability. The evolution of Mars's atmosphere offers a stark contrast to Earth's. Earth's magnetic field and active geology have preserved a dense, life-supporting atmosphere over billions of years. Plate tectonics recycle carbon dioxide, maintaining a stable climate, while the magnetic field shields the atmosphere from solar winds. Mars, lacking these protective and regenerative mechanisms, underwent a rapid decline. By studying these differences, scientists gain a deeper understanding of the delicate balance required for long-term habitability. Mars's atmospheric history serves as a cautionary tale for planets in similar situations. NASA's Mars rovers have been at the forefront of discovering geological evidence that suggests Mars was once a haven for water. Curiosity, exploring Gale Crater, uncovered evidence of ancient lakebeds, The sedimentary layers suggest that liquid water persisted on the Martian surface for millions of years. Clay and sulfate minerals discovered in the crater point to a stable environment with neutral pH levels, ideal for sustaining microbial life. The Perseverance rover, currently exploring Jezero Crater, has expanded on these discoveries. Jezero Crater is home to what appears to be an ancient river delta, a site where water once deposited sediment. Deltas are known on Earth to trap and preserve organic material, making Jezero an ideal location to search for biosignatures. Meanwhile, orbiters have provided a broader context by mapping the planet's surface, identifying widespread hydrated minerals, which are often linked to long-standing water activity and are critical in the preservation of organic compounds. Sedimentary rocks on Mars serve as a natural archive of the planet's history. Mudstones, for instance, form in still water environments such as lake beds and are known to trap organic molecules. Their discovery suggests that lakes on Mars existed long enough to create stable conditions conducive to life. Another critical aspect is the presence of clay deposits, which form through prolonged interaction between water and volcanic rock. Clays are particularly significant because they not only form in wet environments, but also have the unique ability to preserve organic molecules over billions of years. The search for evidence of ancient life has also extended to meteorites. Among the most famous is ALH 84001, a Martian meteorite discovered in Antarctica. This rock contains microscopic structures that some scientists believe resemble fossilized nanobacteria. Additionally, magnetite crystals found within it are arranged in patterns similar to those produced by biological processes on Earth. Perseverance has also begun to examine Martian rocks with textures resembling stromatolites, layered formations created by microbial mats on Earth. While these textures could be geological in origin, their resemblance to Earth's biosignatures makes them compelling targets for future studies. Comparing Martian geological features to terrestrial analogs has been invaluable in identifying potential signs of life. However, interpreting evidence of life on Mars comes with significant challenges. One of the most pressing issues is the difficulty in distinguishing between biological and abiotic processes. Certain chemical reactions involving water and volcanic rock can produce organic molecules or structures that mimic biosignatures. This ambiguity complicates efforts to draw definitive conclusions. Contamination also poses a major hurdle, despite rigorous sterilization protocols. Moreover, the harsh surface conditions on Mars' radiation, extreme cold, and lack of a protective magnetic field make it unlikely that any surface biosignatures would remain intact. The quest for geological evidence of ancient life on Mars is far from over. Perseverance is actively collecting samples that will eventually be returned to Earth through a collaboration between NASA and the European Space Agency. These samples represent our best chance to conduct detailed laboratory analyses. Another exciting new area to explore is the subsurface. Future missions may use deeper drilling technology to access radiation-protected environments where organic molecules and water ice will be retained. Regions with evidence of hydrothermal activity are particularly intriguing, as similar environments on ancient Mars could have been hotspots for microbial life. Venus and Mars, two planets that couldn't be more different today, each hold clues to understanding the delicate balance required for planetary habitability. Venus is a fiery inferno with surface temperatures capable of melting lead, while Mars is a frozen desert. Yet, billions of years ago, both planets may have shared a similar potential for supporting life. What caused their paths to diverge so dramatically? Venus's runaway greenhouse effect. Evidence suggests that Venus once had liquid water, possibly forming shallow oceans that lasted for hundreds of millions of years. However, its proximity to the sun subjected it to intense solar radiation, which began to evaporate its surface water. Water vapor, a potent greenhouse gas, trapped even more heat, accelerating the warming process in a runaway feedback loop. Over time, the planet's oceans boiled away entirely. Ultraviolet radiation from the sun further compounded Venus's problems by breaking apart water molecules in the atmosphere, allowing lighter hydrogen atoms to escape into space and leaving the planet permanently arid. Today, Venus's thick atmosphere of carbon dioxide traps immense amounts of heat, creating a surface temperature hotter than any other planet in the solar system. Mars's atmospheric stripping. Mars, being the fourth planet from the sun, received less sunlight. The presence of ancient riverbeds and lake beds provides evidence that water was able to remain on the surface for extended periods of time due to a formerly thicker atmosphere. But Mars was dealt a poor hand from the start. Being smaller than both Earth and Venus, Mars couldn't hold on to its internal heat or sustain a strong magnetic field for long. Without this protective shield, the solar wind gradually stripped away Mars's atmosphere, leaving it thin and unable to support surface water. Over time, the planet cooled, and its remaining water either froze beneath the surface or sublimated into the atmosphere. The size difference matters when it comes to planetary habitability. Venus and Earth are nearly identical in size and mass, giving them similar abilities to retain atmospheres and sustain internal heat through radioactive decay. This geological activity helps recycle carbon dioxide into rocks and maintain a stable climate. Mars, on the other hand, is much smaller, about half the diameter of Earth, and only 10% of its mass. Its weak gravity made it easier for atmospheric gases to escape into space. Additionally, its smaller size caused its internal heat to dissipate quickly, halting volcanic activity and tectonic processes that could have replenished its atmosphere. Venus's atmosphere is a crushing blanket of carbon dioxide, with a surface pressure 90 times greater than Earth's. This dense atmosphere is both a product and a cause of the planet's extreme heat. Mars's atmosphere, by contrast, is tenuous and thin, with less than 1% of Earth's atmospheric pressure. The differences in atmospheric density and composition between Venus and Mars are critical to understanding why they evolved so differently. While Venus's thick atmosphere fueled a runaway greenhouse effect, Mars's inability to hold on to its atmosphere led to its transformation into an icy wasteland. The distance of a planet from its star also plays a key role. Venus orbits at approximately 0.72 astronomical units from the Sun, placing it on the inner edge of the habitable zone. Mars orbits at 1.52 astronomical units on the outer edge of the Sun's habitable zone. These divergent paths highlight the importance of a planet's position within the habitable zone. As volcanic activity dwindled, so did Mars's ability to maintain its atmospheric density. While Mars's atmosphere is now thin, it remains dynamic. Seasonal dust storms, some of which envelop the entire planet, lift dust high into the atmosphere, accelerating the loss of water by allowing solar radiation to break apart water molecules more efficiently. Furthermore, Mars's polar ice caps, composed of water and carbon dioxide ice, act as seasonal reservoirs for its atmosphere. This cycle affects surface pressure and weather patterns, showcasing the subtle interplay between the Martian surface and its atmosphere. Methane detection on Mars has added a layer of intrigue to the story of its atmosphere. Observations by the Curiosity rover and orbiters have recorded seasonal variations in methane levels. This fluctuation hints at potential geological or even biological sources. Its presence, albeit in trace amounts, raises questions about the planet's past and present habitability. The contrasting fates of Venus and Mars offer valuable lessons for understanding planetary habitability. Venus demonstrates the dangers of being too close to a star, spiraling into uninhabitability through a runaway greenhouse effect. Mars, conversely, underscores the challenges of being too far away. Its inability to sustain complex cycles necessary for life was exacerbated by the absence of plate tectonics and the early cessation of volcanic outgassing. Mars's frigid and lonely path, alongside Venus's blazing wasteland, emphasizes the precarious equilibrium necessary for the emergence and survival of life. By examining the factors that shape them, scientists can refine their models for identifying potentially habitable worlds elsewhere. The discovery of extant life existing today on Mars, would be one of humanity's most profound scientific achievements. It would suggest that life is not an Earth-exclusive phenomenon, but rather a cosmic inevitability under the right conditions. Such a discovery would bolster the theory that Mars was habitable billions of years ago and might have even seeded life on Earth through panspermia. The search for life on Mars has gained momentum thanks to advanced robotic missions. NASA's Perseverance rover, currently exploring Jezero Crater, represents one of humanity's most ambitious attempts. This ancient river delta is an ideal location to hunt for biosignatures, molecular or morphological evidence of life. Perseverance's suite of instruments, including Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, is finely tuned to detect organic molecules and identify potential microfossils. The European Space Agency's Rosalind Franklin rover, slated for a future launch, adds another layer of promise. Equipped with a 2-meter drill, it can access subsurface regions that are better shielded from Mars's harsh radiation, a critical factor since surface conditions might have obliterated any organic evidence. By probing beneath the Martian crust, Rosalind Franklin aims to find preserved organics and analyze their chemical composition using its MOMA, Mars Organic Molecule Analyzer. Detecting life is no small feat. To overcome these challenges, scientists rely on sophisticated techniques to identify biosignatures. The most promising method involves subsurface drilling, as environments shielded by layers of rock and soil offer a refuge where biosignatures might remain intact. Spectroscopy tools aboard rovers analyze the molecular composition of Martian samples to identify carbon-based compounds and differentiate between those formed by biological or non-biological processes. The most likely refuges for extant Martian life are environments that provide stable conditions and access to liquid water. These include subsurface brines, salty reservoirs of liquid water beneath the polar ice caps that remain liquid despite freezing temperatures, and caves and lava tubes, which are insulated from the surface's extreme temperature swings and radiation. Recurring slope, lineae, RSL, dark streaks that appear on Martian slopes during warm seasons, also remain sites of great interest. The quest for extant life will rely heavily on future missions. The Mars Sample Return, MSR mission, aims to retrieve samples collected by Perseverance and return them to Earth for detailed laboratory analysis. These samples could offer conclusive evidence that life exists or existed on Mars. Human exploration of Mars, a goal championed by NASA and private companies like SpaceX, holds the potential to accelerate this search. Astronauts would have the capability to explore diverse terrains, drill deeper, and conduct in situ experiments with greater flexibility. The search for extant life on Mars goes beyond scientific curiosity. It has profound implications for humanity's future. On a practical level, finding life would validate Mars as a potential site for future colonization, where humans could harness resources like water, It also raises ethical questions about planetary protection. How do we ensure that Earth life does not contaminate Mars, and vice versa? On a broader scale, the discovery of life on Mars would redefine humanity's place in the universe, suggesting that life is not unique to Earth, but rather a common outcome of planetary evolution. Mars was at a disadvantage from the very beginning. Its smaller size meant weaker gravity, making it more difficult to hold on to an atmosphere over time. This vulnerability would prove critical as solar winds bombarded the planet, causing lighter elements like hydrogen and helium to escape into space. Earth, with its greater mass, was able to retain its atmospheric integrity. Smaller planets like Mars also cool much faster than their larger counterparts. While Earth's molten core continues to churn, driving volcanic activity and maintaining its magnetic field, Mars cooled rapidly. This early cooling led to the solidification of its core, extinguishing the dynamo effect that generates a magnetic field. Without this protective shield, Mars's atmosphere became even more vulnerable to the sun's relentless winds. Mars's once thick atmosphere was a key player in its ancient habitability, but as its magnetic field faded, the solar wind began stripping away the atmosphere. Data from NASA's MAVEN, Mars Atmosphere and Volatile Evolution spacecraft, left Mars with a thin veil of carbon dioxide, barely sufficient to trap heat or sustain liquid water on the surface. Earth, in contrast, has retained a robust atmosphere. Its magnetic field, generated by the continuous motion of its liquid outer core, deflects harmful solar winds. Beneath Earth's surface, tectonic plates shift and collide, shaping continents and recycling carbon dioxide. This dynamic system plays a crucial role in regulating the planet's climate through the carbon cycle. Mars, however, lacks this vital process. With no active plate tectonics, its surface has remained largely static. Earth's magnetic field does more than deflect solar winds. It also plays a role in protecting the biosphere by shielding the planet from harmful radiation. Mars, after losing its magnetic field, was left exposed to intense radiation, making its surface a hostile environment. Any potential life on Mars would have been forced underground or into transient habitats where protection was available. Mars and Earth share a watery past. Ancient Mars was home to flowing rivers, expansive lakes, and possibly even oceans. Yet, Mars's water slowly escaped into space or became trapped as ice beneath its surface. Earth's water cycle has remained active, driven by the interplay of atmospheric pressure, gravity, and temperature. Mars's lack of sufficient gravity and atmospheric pressure rendered it incapable of sustaining such a cycle, leaving behind dry riverbeds and frozen polar caps as relics of a wetter past. In its youth, Mars was geologically alive, with volcanoes like Olympus Mons and Tharsis Montes erupting with ferocity, reshaping the landscape and contributing to a temporary greenhouse effect. However, as Mars's interior cooled and its volcanic activity ceased, the planet lost this vital source of atmospheric replenishment. Earth, with its larger size and slower cooling rate, continues to experience volcanic activity. This ongoing geological vitality not only contributes to the atmosphere, but also creates diverse habitats. The carbon cycle controls Earth's greenhouse effect, which maintains a mild climate. In contrast, Mars went through a greenhouse collapse. Its thermal capacity decreased as its atmosphere dwindled. As a result of the precipitous drop in surface temperature, the last of Mars's water vapor solidified into the icy desert that we observe today. This striking difference highlights the fine equilibrium needed to keep a place habitable. The sun's energy is a double-edged sword. Mars, being farther from the sun, receives less solar energy, contributing to its colder climate. Earth, positioned in the sun's habitable zone, benefits from just the right amount of energy to sustain liquid water and a stable climate. However, Mars's distance may have initially shielded it from the runaway greenhouse effect that doomed Venus, allowing it a brief window of habitability. Asteroids and comets pounded Mars and Earth throughout the late heavy bombardment. These impacts not only supplied organic materials and water, but they also devastated large areas. Earth was able to heal and reconstruct due to its thicker atmosphere and increased tectonic activity. Because of its thin atmosphere and geologically static surface, Mars had a hard time getting back on its feet, which further limited its capacity for development. Imagine if Mars had been just a bit larger or closer to the Sun, with a stronger gravitational pull and a more robust magnetic field. It might have retained its atmosphere and water, potentially evolving into a lush, habitable world. The divergent paths of Mars and Earth provide invaluable lessons about the delicate interplay of size, distance, geology, and atmospheric dynamics in shaping planetary habitability. Mars and Earth share a unique cosmic relationship, and among the many theories that speculate on the origin of life, one of the most compelling asks whether Mars could have been the cradle of life, seeding Earth as well. This theory, linked to panspermia, suggests that Mars, with its earlier habitable conditions, may have been the first to spark life in our solar system. The early solar system was chaotic. Material regularly traveled between planets. Mars, with its lower gravity and thinner atmosphere, was uniquely positioned to eject fragments of its crust into space during intense bombardments. These fragments could escape Mars's gravity more easily than material leaving Earth, making it plausible for rocks carrying Martian microbes to travel across the void and land on our planet. Studies of Martian meteorites discovered on Earth, including the famous ALH 84001 meteorite, hold chemical fingerprints that confirm this interplanetary exchange. For life to journey from Mars to Earth, it must endure the extremes of space: intense radiation, freezing temperatures, and the vacuum of the cosmos. Remarkably, research on extremophiles organisms that thrive in Earth's harshest environments shows that some life forms might indeed be capable of surviving such conditions. Microbes like Deinococcus radiodurans can withstand high doses of radiation, while tardigrades can enter a state of cryptobiosis. Laboratory experiments have further supported this idea, suggesting that microbial life embedded within rock fragments could survive the violent ejection, the cold of space, and the fiery descent through Earth's atmosphere. These findings reinforce the plausibility of panspermia. This hypothesis is supported by Mars's early start in the race for life. Mars, being smaller, cooled more quickly, allowing it to develop a stable crust and liquid water on its surface much earlier than Earth. During this time, ancient Mars had rivers, lakes, and perhaps even oceans, environments ripe for the emergence of microbial life. Martian material was frequently exchanged between planets during the late heavy bombardment. Given these numbers, it is not far-fetched to imagine that some of these rocks carried microbial passengers. While the idea of Mars seeding Earth is intriguing, it's important to consider the counter-arguments. Earth, with its larger size and more stable conditions, is also a strong candidate for the independent origin of life. Deep-sea hydrothermal vents on Earth provide a compelling model for abiogenesis, the process by which life arises from non-living matter. Some scientists argue that Earth's robust and diverse biosphere indicates an independent origin of life, suggesting that Earth's dynamic plate tectonics and protective atmosphere provided all the necessary ingredients without external influence. The discovery of life on Mars, past or present, would mark a watershed moment in our understanding of the universe. Evidence of life on Mars would shift the narrative dramatically, suggesting that life may not be a rare phenomenon but a natural result of certain environmental conditions. This would challenge the Copernican principle, reinforcing that Earth is not the center of the biological universe. If Earth life originated on Mars through interplanetary seeding, it would revolutionize our understanding of biological lineage. Earth's status as the singular cradle of life in the solar system would give way to Mars, painting the red planet as the elder sibling in the story of life. Alternatively, finding independent life on Mars would suggest that life could arise in multiple places independently, making the galaxy seem infinitely more hospitable. The ethical implications of discovering Martian life are staggering. If life exists on Mars today, humanity must grapple with the morality of further exploration. Would it be ethical to send humans to Mars, potentially contaminating its ecosystem? This raises profound questions about our responsibility as stewards of the cosmos. These considerations extend to legal frameworks, where new treaties may be necessary to ensure that humanity balances exploration with preservation. Some argue that Martian microbes, if they exist, should have intrinsic rights. Mars's history could hold lessons for Earth's future. If Mars once had thriving life that later went extinct, it becomes a cautionary tale of planetary fragility. What led to its decline? The loss of its magnetic field, subsequent atmospheric stripping, or something more catastrophic? Understanding these factors could inform efforts to prevent similar outcomes on Earth. On the other hand, Mars could represent a backup plan for humanity. Discovering life on Mars would also ripple through spiritual and religious communities worldwide, potentially forcing reinterpretations of long-held beliefs. Mars was at a disadvantage from the very beginning. Its smaller size meant weaker gravity, making it more difficult to hold on to an atmosphere over time. This vulnerability proved critical as solar winds bombarded the planet. Smaller planets like Mars also cool much faster than their larger counterparts. This early cooling led to the solidification of its core, extinguishing the dynamo effect that generates a magnetic field. Without this protective shield, Mars's atmosphere became even more vulnerable. Earth, in contrast, has retained a robust atmosphere. Its magnetic field, generated by the continuous motion of its liquid outer core, deflects harmful solar winds. Beneath Earth's surface, tectonic plates shift and collide, shaping continents and recycling carbon dioxide through the carbon cycle. Mars, however, lacks this vital process. With no active plate tectonics, its surface has remained largely static. The absence of tectonics on Mars not only stunted its geological evolution, but also left it unable to recycle key elements needed to sustain a stable atmosphere and climate. Earth's magnetic field does more than deflect solar winds. It also plays a role in protecting the biosphere by shielding the planet from harmful radiation. Mars, after losing its magnetic field, was left exposed to intense radiation. Mars and Earth share a watery past. Ancient Mars was home to flowing rivers, expansive lakes, and possibly even oceans. Yet, Mars's water slowly escaped into space or became trapped as ice beneath its surface. Earth's active water cycle has remained stable over billions of years. Mars's lack of sufficient gravity and atmospheric pressure rendered it incapable of sustaining such a cycle, leaving behind dry riverbeds and frozen polar caps as relics of a wetter past. In its youth, Mars was geologically alive, with volcanoes like Olympus Mons and Tharsis Montes erupting with ferocity, contributing to a temporary greenhouse effect. The profound implications of discovering life on Mars extend far beyond the laboratory. For some, the evidence could prompt a re-examination of humanity's role in the cosmos, perhaps even diminishing Earth-centric spiritual and philosophical views. Conversely, the discovery could unify humanity. Realizing that life exists beyond Earth might inspire a collective sense of awe and humility. Fostering a global perspective, it could remind us that we are all part of a shared journey in a vast, interconnected universe. In this way, Martian life might become a unifying force, bridging divides and inspiring a sense of common purpose. The discovery of life on Mars would signal a new chapter in human history. It would mark the moment humanity transitioned from an Earth-bound species to one capable of exploring and potentially interacting with alien biospheres. This transition would fundamentally redefine human identity. We would no longer be solely Earthlings. We would become interplanetary beings with responsibilities and opportunities that extend far beyond our home planet. Mars would inspire a new wave of literature, art, and philosophy, just as the moon landings in 1969 inspired a generation. The discovery of life on Mars could spark a renaissance of creativity and innovation. It could lead to new ways of thinking about coexistence, not just with other humans, but with entirely alien life forms. Mars's history has the potential to alter Earth's as well. Human and biological history would be entirely rewritten if life on Mars first emerged and then made its way to Earth. It would show that life can persist in the face of adversity, highlighting the interdependence of all worlds within the solar system. The discovery of life on Mars would instantly redefine the search for life elsewhere. If life arose on both Earth and Mars, it would suggest that the conditions for life are not as unique as we once thought. This would shift the focus of exploration to other solar system bodies, such as Europa, Enceladus, and Titan, and even to exoplanets orbiting distant stars. Mars would serve as a stepping stone, providing a blueprint for identifying life in other extreme environments. Technologically, Mars's discoveries could accelerate advancements in space exploration, from improved drilling techniques for subsurface biosignatures to advanced life detection instruments. The tools developed for Mars could be adapted for use on other worlds. These innovations would bring us closer to answering one of humanity's oldest questions: are we alone? If Mars once supported life, it would reinforce the idea that life is resilient and adaptable. It thrives in conditions we might consider inhospitable, from the acidic waters of Earth's volcanic springs to the icy subsurface oceans of Jupiter's moons. Mars would serve as a testament to life's tenacity, expanding our understanding of what is possible in the universe. A number of issues about planetary connectivity have been brought up by Mars's narrative. Are Mars and Earth really two distinct worlds? Or are they rather nodes in a common biological network? Assuming life does or did exist on both of these planets, this theory posits that the planets are not completely separate from one another, but rather that they are all involved in complex cosmic webs. The potential extinction of Martian life also serves as a sobering reminder of life's fragility. It underscores the delicate balance required to sustain a biosphere and highlights the importance of preserving Earth's environment. Mars's history could become a symbol of what happens when a planet loses its ability to support life. The ethical implications of discovering Martian life are staggering. If life exists on Mars today, even in microbial form, humanity must grapple with the morality of further exploration. Would it be ethical to send humans to Mars, potentially contaminating its ecosystem? This raises profound questions about our responsibility as stewards of life in the solar system. These questions will shape the future of space exploration and define humanity's relationship with the universe. The issue of planetary protection is paramount. We must ensure that Earth life does not inadvertently contaminate Mars, forward contamination, and conversely, that any Martian life returned to Earth does not pose a threat to our biosphere, backward contamination. This concern has driven the meticulous design of the Mars Sample Return mission. The complexity of this mission underscores the seriousness with which the scientific community treats the possibility of alien life. Some argue that Martian microbes, if they exist, should have intrinsic rights, preventing humans from exploiting or interfering with their habitat. These considerations extend to legal frameworks. New treaties may be necessary to ensure that humanity balances exploration with preservation. The discovery of Martian life would leave an indelible mark on future generations. It would inspire long-term investments in science, education, and space exploration, laying the groundwork for humanity's next great leap. Mars would become a symbol of what humanity can achieve when it works together, fostering a sense of global unity. Perhaps the most profound question Mars poses is, who are we? If life originated on Mars and spread to Earth, it would mean that we are, in a sense, Martians. This realization would challenge our identity as Earthlings and force us to consider our place in the broader cosmic tapestry. Mars also makes one wonder why we're here. Does the very fact that we exist depend on chance and fate, or is it a universal occurrence that follows the rules of the cosmos and cannot be prevented? Mars could help us get closer to the answers to these issues that have plagued humanity for thousands of years. Mars's history may even provide light on the so-called Great Filter, a theoretical barrier that explains our lack of contact with advanced alien cultures. If all life on Mars were to suddenly end because of a catastrophic environmental breakdown, it may show us how difficult it is for any kind of life to stay alive and evolve beyond a certain stage. This concept suggests that life is either incredibly rare, an early filter, or that advanced civilizations inevitably destroy themselves, a late filter. The Martian narrative, pointing to an early environmental collapse, offers a potential glimpse into that early barrier. At its core, Mars is a philosophical benchmark rather than merely a scientific one. Its narrative goes beyond facts and theories to provide a prism through which people may consider their place in the universe, their own identity, and what the future holds. The journey to uncover Mars's secrets is far from over, and upcoming missions are poised to take our understanding to new heights. The NASA and ESA Mars Sample Return mission stands out as a groundbreaking endeavor. This ambitious multi-phase project involves collecting and transporting Martian soil and rock samples back to Earth for in-depth analysis. These samples, currently cached by the Perseverance rover, will undergo scrutiny with instruments far too large or complex to send to Mars, potentially revealing traces of ancient microbial life or confirming the presence of organic molecules with unprecedented precision. The Rosalind Franklin rover, a flagship mission under the ExoMars program, is another key player. Named after the scientist who contributed to the discovery of DNA structure, this rover is uniquely equipped to drill up to 2 meters below the Martian surface. This capability is critical since the surface is bombarded with radiation, making it inhospitable to life as we know it. By exploring subsurface regions, the rover may uncover well-preserved biosignatures in ancient sediments. Next-generation orbiters like the Mars Ice Mapper will focus on surveying subsurface ice reservoirs, Understanding these reserves is crucial not just for scientific knowledge, but for the practicalities of future human missions. Such discoveries could revolutionize our understanding of water cycles on Mars and serve as essential resources for sustained human presence. Private companies, too, are making strides. SpaceX, with its bold vision of colonizing Mars, is developing reusable spacecraft capable of transporting humans and cargo. While its primary goal is to establish a self-sustaining Martian colony, the infrastructure it creates could provide unparalleled opportunities for scientific exploration. The field of astrobiology has seen remarkable advancements, many of which are directly applicable to Mars exploration. Biosignature detection remains a top priority, with cutting-edge instruments designed to identify isotopic patterns or molecular structures indicative of biological processes. For example, next-generation spectrometers can detect subtle variations in carbon or methane isotopes that might suggest biological origins. Robotic missions, as advanced as they are, have limitations. Human exploration could transform Mars science by introducing adaptability, intuition, and the ability to make real-time decisions. Astronauts could explore regions inaccessible to rovers, rapidly adjust plans based on observations, and conduct experiments on site. The capacity to go further into the Martian subsurface is one of the greatest benefits of human exploration. Human crews using sophisticated equipment might reach strata tens of meters deep, where remnants of ancient life may be preserved. Exploring Mars also provides a stark reminder of our planet's fragility. Mars, with its desolate landscapes and once vibrant history, shows us the importance of protecting Earth's ecosystems. Understanding what went wrong on Mars could help us avoid similar fates on our home planet. Throughout human history, the quest to understand where we come from has been as much about looking outward as inward. Among all celestial bodies, Mars has emerged as a focal point of this search, tantalizing us with its secrets and possibilities. Could life have started there on the Red Planet and somehow found its way to Earth? Or might the ancient rivers and lakes of Mars tell a parallel story of a world that could have been, had circumstances aligned just a little differently? As we draw to the end of this exploration, let's reflect on the profound implications of our ongoing investigation into the Red Planet. Mars, long a symbol of mystery and exploration, has consistently drawn humanity's attention not just for its proximity, but for its striking similarities to and differences from Earth. It was once a world of rivers, lakes, and even oceans, holding the key ingredients for life as we know it. From studying its lost atmosphere to analyzing the mineral-rich terrain and its long, dormant volcanic activity, Mars offers an invaluable lens into the potential origins of life in our solar system. Theories such as panspermia and the interplanetary exchange of meteorites challenge the idea of Earth as an isolated cradle of life. The discovery of organic molecules, the evidence of ancient water, and even the detection of methane fluctuations suggest a planet that was once alive in ways we are only beginning to understand. The idea that life may have arisen in Mars's lakes or hydrothermal vents, evolving before Earth's chaotic environment settled into stability, is staggering. Whether life began on Mars or not, the Red Planet remains a critical piece of the puzzle in understanding life's potential in the universe. Its history reminds us that habitability is not just about water or even the right chemical ingredients, but about the delicate balance of planetary conditions. The story of life's origins is far from complete, but each new discovery on Mars brings us closer to answering the ultimate question: are we alone, or are we part of a cosmic family, connected by the threads of life that began far beyond our home?